Welcome to the final presentation about the results of the project MEMPHIS 2. MEMPHIS 2 stands for Methodology to Evaluate and Map the Potential of Waste Heat from Industry, Service Sector and Sewage Water by using internationally available open data. My name is Johannes Pelder and I am a research assistant at the University of Applied Sciences and Arts in Göttingen, Germany. On behalf of the project team, I'm pleased to present the results of the MEMPHIS 2 project. The project was carried out between August 2021 to January 2023 and funded under the IEA Annex XIII. It bases on and improves the results of the former project MEMPHIS. In the project, the waste heat potentials of industrial processes and of wastewater in the sewer network were considered. An online tool provides technical and economic analysis of waste heat recovery systems that can be individually designed. The following improvements were developed in the follow-up project. Determination of the temporal availability of the waste heat potential. A tool defining the technical design and rapidly evaluating business potentials of assessing waste heat sources by tailor-made assessments. Adding prospective waste heat sources to the Waste Heat Explorer. Expanding the Waste Heat Explorer to 3 Italian cities. Partial validation of the available data with the target of carrying out at least 3 comparisons between real data and the estimates provided by MEMPHIS 2. With a newly developed simulation model, temperature gradients as well as the origin of the wastewater flows can be calculated within a sewer network by using open data. Furthermore, the simulation model enables optimization to be carried out in order to find the best technical location for waste heat extraction from the sewer. The analysis of the cost competitiveness of different sustainable heat supply technologies show that the average levelized cost of heat, LCOH, of these technologies was in 2020 about 68 euros per megawatt hour, which is roughly 3 times higher than the average LCOH of fossil-fired plants. The number of full load hours has the greatest impact on costs, followed by the investment cost of the heat pump and the electricity price. At this slide, you can see the waste heat potential summarized for the 5 cities. The potential of waste heat from wastewater taken within the city limits is seen in the blue bars. The orange bars indicate the potential at the entrance of the wastewater treatment plant. The x-axis shows the scenarios that differ in the minimum heat extraction rate. As the extraction power increases, the total energy decreases, but the temperature in blue dots at the point of the heat extraction increases. The temperature at the inlet of the treatment plant remains constant. The diagrams show the annual absolute waste heat potential and the potential related to the local district heating network. In the cities of Göttingen, Ospitaletto and Trento, the theoretical waste heat from sewer could supply more than 100% of the district heating demand, seen in the green dots for the inlet at the wastewater treatment plant and the blue bars within the city's limits. In this diagram, the profitability of the waste heat recovery system is taken into account the electricity price and the heat price. With a target profitability of 10% and an electricity price of 122 euros per megawatt hour, the selling price of the heat must be more than 152 euros per megawatt hour, seen at the green dot. The left diagram shows the results of the impact of technical or economic parameter changes on the LCOH. It is evident that changes in the number of full load hours have the strongest influence, followed by the investment costs of the heat pump and the electricity price. With each adjustment in the full load hours by a factor of 1/10, the LCOH varies on average by approximately 17 euros per megawatt hour. Adjusting the investment cost of the heat pump by 1/10, the LCOH increases by 5 euros per megawatt hour, and adjusting the electricity price by 1/10, the LCOH increases by 4.6 euros per megawatt hour. Key achievements include an assessment of the impact of industrial decarbonization on waste heat potentials. The analysis was carried out on a qualitative basis for cross-section technologies and processes, for instance, exhaust gas or the cooling of process media, and on a quantitative basis for the iron, steel, and cement sectors. It revealed that, depending on the processes in an industry sector, changes in both directions are to be expected. For example, the electrification of combustion processes omits the waste heat from exhaust gas streams, while the decarbonization in the cement sectors relies on the deployment of carbon capture technologies with additional waste heat streams. In terms of assessing upcoming waste heat sources, a strong focus was laid on electrolyzers. The analysis revealed that waste heat potential of up to 250 terawatt-hour annually within the EU 27 plus UK by 2040. This equates to a 64% of the projected heat demand supplied by district heating networks. The graph on the right side depicts the waste heat potentials and district heating demands broken down on a national level. It can be seen that there are countries where the expected waste heat potential from electrolyzers is greater than the district heating demand. In terms of improvements within the Waste Heat Explorer, a techno-economic assessment feature was implemented. The methodology covers needed components for the waste heat utilization like heat transfer stations, buffer storages, district heating piping, and optional seasonal storages. Furthermore, it designs these components based on the chosen waste heat source and the user input on heat sink parameters. With the input of a few parameters specifying the heat sink such as its annual heat demand, temperature requirements, and the costs for heat supply with a reference system, and the drawing of the desired pipe route between source and sink, a quick assessment of the economic feasibility is performed. The user receives an immediate feedback on the screen with the key results of the calculation and has the possibility to download a report with all the information on the assessment. The picture on the right depicts the implemented tool and shows results of an example calculation. A final achievement of the project is the investigation of further 3 cities in Italy and the validation of the methodology with real data on industrial facilities. During the project, the data for all industrial companies in the 3 cities, Ospitaletto, Bolzano, and Trento, were collected through interactions with the local chambers of commerce. The data include company location, number of employees in the industrial sector. In order to insert reliable information in the Waste Heat Explorer, some data preparation and cleaning was needed. In particular, filters and other checks were required for companies with a limited number of employees or multiple sectors. The available data were then validated for selected cases, namely a foundry in Ospitaletto, a dairy, a vehicle manufacturing company, and a printing company in Bolzano, and finally a supermarket in Trento. Waste heat estimates based on MEMPHIS coefficients were generally confirmed. Only in one case, namely that of the dairy located in Bolzano, a strong deviation was observed. Here, the value estimated from company data turned out to be about 10 times higher than the one predicted by the algorithm. Let me summarize. MEMPHIS II is an advanced project that builds up on the previous MEMPHIS initiative with a focus on evaluating and mapping the potential of waste heat from industrial processes, the service sector, and sewage water by using open data and service. In particular, MEMPHIS II has developed a simulation model that calculates temperature gradients and wastewater flows within a sewer network and is the basis for optimizing the location for waste heat extraction. The project also assesses the cost competitiveness of sustainable heat supply technologies, highlighting the impact of the number of full load hours, heat pump costs, and electricity prices on the levelized costs of heat. Additionally, MEMPHIS II looks into temporal availability of waste heat from industrial processes, noting variations in waste heat potential during week and days, but not seasons. It also highlights the upcoming potential of waste heat from data centers and electrolysis processes that will further increase in the future. The Waste Heat Explorer significantly developed during the project, providing data on wastewater origin, temperature, and seasonality, along with information about industrial waste heat. It offers a routing function for connecting waste heat sources to heat sinks and conducts automatic techno-economic evaluations, which are free for download. The newly added techno-economic assessment feature allows for a quick indication on the feasibility of a dedicated waste heat utilization project. Furthermore, data from industrial companies in Italy cities has been collected and validated, contributing to the project's comprehensive dataset. The project's holistic approach to assessing and using waste heat contains important information that can serve as a starting point for developing sustainable energy solutions. Of course, more detailed checks are recommended before the actual design work. Finally, concerning the validation process, it is worth observing that it involves rather time-consuming individual contacts. Hence, getting data samples large enough to provide statistically meaningful results is quite challenging. Due to the increasing relevance of waste heat in the future energy system, it might hence be worth discussing about policies where data collection is made more automatic and easily accessible, as the needed information does not exhibit a significant confidentiality level. Here you will find the final project report, the Waste Heat Explorer, and more information on our website. Thank you for your attention. If you have questions about the project, please feel free to contact me via my email address.